Okay, so get this. Imagine a universe, right, where instead of a big bang, you have a big bounce and black holes. They're not just these like dead ends, but they actually hold secrets about about the universe's entropy.
Whoa.
Wild, right?
Yeah.
That's what we're diving into today. Loop quantum gravity.
Yeah, it's a pretty ambitious theory. It's really trying to bridge two of the biggest ideas in physics, Einstein's general relativity and quantum mechanics.
And we've got a guide for this journey using excerpts from a first course in loop quantum gravity. But before we go too deep into the weeds, I kind of want to like take a step back.
Sure.
Why is this even necessary? General relativity and quantum mechanics, they're both like incredibly successful in their own domains, right?
They are, but they really clash when you try and describe the universe at its most extreme points,
Okay.
like the Big Bang
Mhm.
or the singularity at the heart of a black hole. And that's where we need a theory of quantum gravity.
Okay, so how does loop quantum gravity tackle this? Is it trying to like be a theory of everything?
It's interesting because uh, unlike some other approaches, loop quantum gravity actually just focuses on gravity directly.
Okay.
And it suggests quantizing gravity, which essentially means breaking it down into its smallest possible bits.
Okay, so like how energy comes in these tiny packets called quanta.
Right.
Loop quantum gravity is saying space-time is made of like tiny little pieces.
Yeah, that's the idea.
Uh-huh.
And general relativity is all about the curvature of space-time,
Right.
like a bowling ball on a trampoline.
Yeah, yeah.
But loop quantum gravity says that space-time isn't this smooth sheet. It's more like a fabric, a finely woven fabric.
Okay, so I'm picturing like a tiny quilt
Uh-huh.
making up the universe. But what are the like the threads of this quilt made of?
Well, loop quantum gravity uses something called holonomies. You
Holonomies.
can think of it as imagine you're an ant walking on a curved surface.
Okay.
To measure that curvature, you can walk in a loop and see if you end up back where you started.
Right. If it's flat, you'd end up in the same spot. But on a curved surface, you might be like a little bit off.
Exactly. And in loop quantum gravity, these holonomies, they measure the curvature of space-time, but along these loops.
Okay.
And those loops connect to form what we call spin networks.
Quantum network. So it's like
Okay.
each loop is a measurement of the curvature.
Yes,
And then the spin network is this whole map of how space-time is shaped.
you got it. And these networks, they actually look like graphs with lines of different colors, and each line represents a loop carrying a specific amount of area.
Wait, so the lines have like colors?
They do.
That's so cool.
Yeah, it's a good way to visualize it. It helps you see how those fundamental bits of area are connected.
Right.
And now, because space-time is built from these tiny pieces, discrete pieces, it means that there's a limit to how small things can actually get.
Hold on. So you're saying there's a smallest possible like chunk of space.
Yeah.
Can you like give me an example?
So imagine you're trying to slice a piece of paper in half,
Huh.
and then in half again and again and again forever.
Yeah.
Loop quantum gravity says you're going to reach a point where you just can't divide it anymore.
Wow.
It's the smallest possible piece of area.
So there's like a fundamental limit. You can't go smaller than that.
That's right.
That's crazy. So how does this quantum geometry, I like that,
Yeah.
change our view of the universe, especially when it comes to the very beginning, the Big Bang?
Yeah, that's where things get really interesting.
Okay.
That's where we get into loop quantum cosmology.
Right.
And it tells a very different story about the origin of the universe.
Okay.
So in general relativity, the Big Bang starts with a singularity,
Right.
that point of infinite density.
Yeah,
But loop quantum gravity says, not so fast.
it does.
Yeah, as the universe contracts in loop quantum cosmology, it reaches a point where the quantum nature of space-time really takes over.
Oh, okay.
And instead of collapsing into a singularity, it bounces back, which leads to a big bounce instead of a big bang.
Okay, I'm starting to see how this theory really like shakes things up.
It does.
But what about black holes? Does loop quantum gravity change how we think about those too?
Absolutely. It offers a completely different perspective on one of the biggest puzzles in physics, the black hole information paradox.
Yeah, and I've always found that to be like one of the most frustrating things in physics. If nothing can escape a black hole, where does the information go?
Yeah, it bothered physicists for a long time.
Yeah.
But loop quantum gravity suggests that black holes aren't these information-destroying monsters that we once thought they were.
Okay.
And it suggests that they might actually have a finite amount of entropy.
So you're saying that black holes have like some sort of structure to them, some way of like holding information?
Yeah, that's what the theory suggests.
Yeah.
It proposes that the entropy of a black hole, which is a measure of its disorder, how many possible arrangements there are inside,
Okay.
is proportional to its surface area.
So instead of being these like featureless voids,
Right.
they have a certain like information capacity
Yes.
determined by their size.
Exactly. And what's really cool is that calculations in loop quantum gravity connect that microscopic structure of those spin networks at the horizon to its entropy.
So we're potentially like solving this information paradox.
It's one of the ways that it tries to address it.
That's wild. So black holes might not be the end of the line for information, huh? But if their entropy is finite, does that mean they can eventually like disappear?
That's a great question, and it takes us even deeper into this whole idea of black holes and something called Hawking radiation.
Ooh, okay. I think we need to give our listeners a moment to like let all this sink in. We'll be right back with more of our deep dive into loop quantum gravity.
So before the break, you were asking about whether black holes can actually disappear.
Yeah, yeah.
And the answer might surprise you.
Okay.
Even without loop quantum gravity, there's this idea called Hawking radiation.
Right. Hawking radiation, I've heard of it,
Yeah.
but it always seemed kind of like counterintuitive to me.
Yeah. How can something escape from a black hole if not even light can get out?
Right, right. It's a real head scratcher.
Yeah.
But the key to understanding this is it all comes down to quantum mechanics,
Okay.
which suggests that even in the vacuum of space, you have these virtual particle pairs
Okay.
that are constantly popping in and out of existence.
Mhm.
They borrow energy from the universe and then very quickly annihilate each other.
So like little loans of energy that have to be paid back immediately?
Exactly. That's a good way to think about it.
Okay.
But near a black hole's event horizon, things get really weird.
Okay.
Sometimes one of these virtual particles gets pulled into the black hole,
Oh, okay.
while the other one manages to escape.
And that becomes Hawking radiation?
That escaping particle becomes Hawking radiation.
Wow, okay.
And because it escapes, it carries away a little bit of the black hole's energy. And over vast, vast timescales, this slow leak can actually cause the black hole to shrink and maybe even vanish completely.
So black holes aren't eternal then? It seems that way.
Wow. That's wild.
Now, where does loop quantum gravity fit into all of this?
Yeah.
Remember those spin networks?
Yeah.
The ones that describe the quantum states of space-time at the black hole's horizon?
Yeah.
Well, loop quantum gravity can actually provide a possible explanation for the microscopic origin of black hole entropy.
Okay, so instead of just saying black holes have entropy, loop quantum gravity is actually telling us what's creating that entropy at the smallest level.
Exactly.
Okay.
It's like counting up all the different possible configurations of those spin networks at the horizon,
Okay.
each one representing a unique quantum state of the black hole.
Right.
So the more arrangements you can have, the higher the entropy.
Yeah. Okay, that makes sense.
And the amazing thing is that calculations from these two very different perspectives, the thermodynamic view from general relativity and the microscopic view from loop quantum gravity, seem to match up incredibly well,
Huh.
which gives us some confidence that loop quantum gravity might be onto something.
That's pretty cool.
It is.
But, we've been talking about some pretty, like, out there concepts.
Right.
How can we be sure that loop quantum gravity isn't just a really nice mathematical theory,
Sure.
but actually an accurate description of, like, the real world?
Yeah.
Are there ways to actually, like, test it?
That is the million-dollar question.
Yeah.
And it's one that physicists are really actively working on.
Okay.
One promising avenue is to look for the effects of this grainy space-time on light itself.
Okay, like how light behaves differently when it passes through a prism.
Yeah, it's a similar idea.
Okay.
Some researchers believe that the discrete nature of space-time in loop quantum gravity could cause light of different colors to travel at slightly different speeds.
Oh.
And this is an effect called birefringence.
So like a cosmic prism, kind of?
Yeah, like a cosmic prism.
Splitting the starlight based on the quantum structure of space-time.
Yeah, that's the idea.
That's wild.
Yeah, it is.
But wait, haven't we like observed light from distant galaxies and quasars and stuff? Shouldn't we have seen this already?
It's not that simple, unfortunately.
Okay.
This effect is predicted to be unbelievably tiny, like on the order of the Planck scale,
Right.
which is way, way beyond the sensitivity of our current telescopes and instruments.
So we need like even better tools to be able to see these effects.
You need much more sensitive instruments.
Okay.
But there's another exciting possibility, and that's looking at the cosmic microwave background radiation,
Oh, right, right.
the afterglow of the Big Bang,
Yeah, the oldest light in the universe.
the oldest light in the universe.
Could that hold, like, clues about loop quantum gravity?
Some physicists think so.
Okay.
They believe that these quantum effects near the Big Bounce might have left a unique fingerprint on the cosmic microwave background.
So, like, looking for ripples in the cosmic pond,
Exactly.
traces of those early moments when quantum gravity was, like, really important.
That's a great way to put it.
Okay, so we'd be analyzing these patterns in the cosmic microwave background. And that could tell us something about loop quantum gravity.
It could.
And maybe even provide evidence for the Big Bounce.
It's possible.
That's amazing, but haven't scientists, like, been studying the cosmic microwave background for a long time already?
They have, but it's a real needle in a haystack.
Okay.
The signal is incredibly faint,
Right.
and it's buried within a lot of other noise from, other cosmological events.
Right, right.
But our tools are constantly improving, so there's hope that we'll eventually be able to pick out those whispers of quantum gravity.
I hope so.
Me too.
It sounds like a lot of the focus is on observing the cosmos
Right.
to try and find evidence for loop quantum gravity.
Mm-hmm.
Are there any ways to study it, like here on Earth?
That's a great question, and it pushes the boundaries of what we can do experimentally.
Okay.
We talked about those challenges of unifying general relativity and quantum mechanics in extreme environments,
Right, right.
like black holes.
Yeah.
Well, some physicists are actually looking into simulating certain aspects of loop quantum gravity
Okay.
using highly controlled quantum systems, things like ultra-cold atoms.
So they're trying to build like a quantum sandbox
That's a good way to put it, yeah.
where they can kind of like recreate the conditions that might exist near a black hole or the early universe.
Yeah, and try and understand how space-time behaves at that quantum level.
Wow, that's incredible.
It's very ambitious, but it could provide some really valuable insights.
Yeah.
And maybe even let us test some of loop quantum gravity's predictions in a much more controlled way.
Wow, it seems like physicists are like really pulling out all the stops
They are.
to try and figure this out.
Absolutely.
So what's next for loop quantum gravity?
Mhm.
What are the big questions that still need to be answered?
There are many, many.
Yeah.
But I think one of the most fundamental and challenging ones is the problem of time.
The problem of time. What do you mean?
I know, it seems like the most basic and intuitive concept.
Right, yeah.
But time is a real headache for physicists,
Okay.
especially when you try and reconcile general relativity with quantum mechanics.
Okay, so how do the two theories view time differently?
So in general relativity, time is woven together with space
Right.
to form this four-dimensional space-time continuum.
Yeah.
It's relative. It can be warped by gravity.
Right.
But in quantum mechanics, time is treated as this absolute external parameter,
Okay.
a kind of unchanging backdrop against which everything else unfolds.
Oh, okay. So it's like the two theories are using different operating systems for time.
That's a really good way to put it, yeah.
Okay.
And trying to figure out how to merge those two is a major puzzle for any theory of quantum gravity,
Including loop quantum gravity.
including loop quantum gravity.
So loop quantum gravity has to not only quantize space,
Yes.
but also like grapple with the nature of time itself.
It does.
Whoa. Okay, now we're getting into like really deep philosophical territory.
We are. And the answers to these questions are going to have a profound impact on how we view the universe
Absolutely.
and our place within it.
Yeah. Okay, my brain is officially fried.
I know, it's a lot to take in.
We've covered so much.
Wow.
Black hole entropy, the problem of time, but it feels like there's still so much more to explore.
There is. And
Yeah.
we'll be back after a short break
Okay.
to delve into some of the criticisms and open questions surrounding loop quantum gravity,
Okay.
as well as some even wilder ideas about the very fabric of reality.
Ooh, stay tuned. Okay, so we're back and ready to talk about the kind of the tougher side of loop quantum gravity, the criticisms and the questions that are still out there.
Right. Every great theory faces some challenges.
Yeah, exactly.
Loop quantum gravity is no different.
Okay, so what are some of the main criticisms?
Well, one of the big ones is that, we've got this amazing picture of quantum space-time,
Right.
but connecting it back to the everyday world of classical physics
Yeah.
hasn't been that straightforward.
So how do we go from like a universe made of loops and spin networks to the the smooth space-time that we experience, you know?
Yeah, it's like we're missing a bridge between those two pictures.
Yeah, exactly.
And this is what we call the semi-classical limit.
Right.
It's showing how that quantum world transitions to the classical one.
Okay.
And it's an area where loop quantum gravity still has some work to do.
So critics are basically saying, like, it's not clear how this, like, pixelated space-time
Right.
averages out to the smooth universe that we see at larger scales.
That's one of the challenges. Another is that, while it's done a great job describing the structure of space-time at the quantum level,
Right.
we call the kinematics,
Yeah.
nailing down the dynamics, so how this structure actually changes over time, has been trickier.
Okay, I need a quick refresher.
Sure.
What's the difference between kinematics and dynamics?
So think of it this way. Kinematics is like taking a snapshot of space-time.
Okay.
You're just capturing its properties at that moment.
Right.
Dynamics is like watching a movie.
Okay, yeah.
It's understanding how space-time changes and interacts over time.
So we've got a beautiful picture, the snapshot, but we're still working on the movie, the rules of the movie.
Exactly. And this is where this thing called the Hamiltonian constraint comes in,
Right.
which is essentially the equation that governs how this whole system evolves in time.
Okay, so like the rule book for space-time, but you're saying there's like debate about how to actually write this rule book.
Yes. Defining the Hamiltonian constraint in a way that makes sense both mathematically and physically has been really hard.
So there are like multiple possible movies, but we don't know which one is playing in our universe.
It's definitely a challenge.
Okay.
It leads to another criticism, which is this issue of ambiguities.
Okay.
There are different ways to actually define this Hamiltonian in-loop quantum gravity.
Right.
And it's not always clear which choice is the right one.
So how do physicists deal with those ambiguities? Are they like a deal breaker for the theory?
Not necessarily.
Right.
Some of them might be resolved by adding more constraints,
Okay.
Either physical or mathematical constraints,
Right.
while others could actually reflect real choices in how we describe the quantum world. It's definitely an ongoing area of research.
So not a fatal flaw, but like something to be worked on.
Right.
Okay, but even with these criticisms, it sounds like loop quantum gravity is still a very like a lively field of research.
It really is.
Yeah.
Physicists all around the world are trying to address these open questions
Right.
and refine the theory. It's very dynamic and evolving.
And speaking of evolving, we got to talk about spin foams.
Yeah.
They sound like something out of a sci-fi movie.
They do.
What are they?
So if spin networks are the individual frames of our space-time movie,
Okay.
then a spin phone is like the entire film reel.
Right.
It captures the evolution of space-time over time.
So like a 4D version of a spin network.
Exactly.
Showing how those loopy structures like change and interact with each other.
Yeah, so picture a network of interconnected bubbles,
Okay.
and each bubble represents a quantum transition of the spin network.
So each bubble is like a fundamental event in the history of space-time.
That's a great way to think about it.
A quantum leap in the structure of the universe.
Yeah, and calculating these spin foam histories lets physicists explore different possible scenarios for how the universe evolved at the quantum level.
That's pretty wild. We're really looking at like the quantum code of the universe here.
In a way, yes.
But can we like zoom out for a second
Sure.
and talk about why loop quantum gravity is important? Why
Yeah.
should we care?
Well, loop quantum gravity is it's not just about these abstract equations and concepts. It's really about tackling some of the deepest questions humans can ask.
Right.
What is space?
Yeah.
What is time? What are the building blocks of reality?
It's a quest to understand, like the very essence of the universe.
Exactly.
Crack the code of existence.
And the potential payoffs are huge. Not only could it solve mysteries like the Big Bang singularity, the black hole information paradox,
Right.
but it could also completely revolutionize how we understand the universe.
Yeah.
And lead to new technologies that we can't even imagine right now.
It's like a journey into the unknown, but it's full of possibilities.
Exactly.
And it feels like we've only just like scratched the surface of loop quantum gravity.
We really have. And we encourage you, the listener, to keep exploring.
Yes.
There are so many resources out there to delve deeper into this really fascinating field.
Absolutely.
And who knows, maybe you'll be the one to make the next big breakthrough in loop quantum gravity.
That's a great thought to end on. This deep dive has been amazing. Loops, spin networks, the quantum nature of space-time. I definitely have a lot to think about.
It's been a pleasure exploring it with you.
Well, thanks for joining us on this incredible journey through loop quantum gravity.